Hello students, welcome to FosterJEE. This is our second lecture for chapter Current Electricity. In our last lecture, we have discussed some basics of current in conductor and also a basic idea about resistance. Now, you were given a problem for homework to solve. So let's see. And the problem was, if the current in a wire increases uniformly from 2 ampere to 3 ampere in 5 seconds, what is the amount of charge flown through the wire during this time interval? Now in the last lecture also, we have seen that many times in the question there will be given words like physical quantity is increasing uniformly or at a constant rate or else linearly. And I have suggested you that in such cases, always try to write the equation of line. So we have seen that we can see increases uniformly. That means there will be a linear relation from 2 to 3. So let's see how we will tackle this problem. First of all, we will draw graph between the changing quantities. Let's take current I on y-axis and time t on x-axis. Now we are given that if the current in the wire increases uniformly from 2 ampere to 3 ampere, that is initially, that is at time equal to 0, the current was 2 ampere. And after 5 seconds, the current increases uniformly to 3 amperes. This is 3 amperes. Now, if we are able to find the equation of this line, then we can get the variation of current with time. Now let's see. We know the coordinates of this point is 0, 2, and so of this point is 5, 3. Any line can be represented in a form of y equals to mx plus c. That's right solution. Let's put our first point in this line. We will get, in place of y, we will get 2 is equal to 0 plus c, which implies c is equal to 2. Let's put the second point. We will get 3 is equal to m times of 5 plus c, that is 2. The value of m comes out to be 1 upon 5. Hence the equation of line is y equals to 1 by 5 x plus 2. In place of y we have current and in place of x we have time. So I will be t by 5 plus 2. Hence we are able to get the variation of current with time. Now simply we have to calculate the total charge flown through the wire during this time interval. Now we know current is dq by dt, and the value of current is t upon 5 plus 2. If we want to calculate the total charge dq, then let's take t on that side, and this becomes t upon 5 plus 2 into dt. For getting the total charge accumulated at t equal to 0, there was no charge accumulated initially, and at time t equals to 5 seconds, the total charge q is to be evaluated. So the value of q will be t square by 5, 2 into 5 plus 2t. On putting the limits 0 to 5, we will get 5 square upon 10 plus 10. This comes out to be 12.5 coulomb. So in this time interval, a total of 12.5 coulomb charge is flown through the wire. So this is a very important type of problem which we will tackle many a times in physics. So we have to remember that in place of uniformly, linearly, or at a constant rate, we can simply write the equation of the line and then proceed like this. Now let's move to our next topic, which is drift velocity, and relaxation time. Now we have already discussed about drift velocity, which is the velocity with which electron collides with another electron in order to transfer energy. Now let's understand what is this relaxation time. We will write topic relaxation time. It is denoted by tau and it is defined as the average time between two successive collisions. Now we know, suppose we have 3 electrons in a row. Just to understand this model, we'll take 3 electrons. Now suppose this electron got its kinetic energy from this side and it will transfer its kinetic energy from this electron to this electron. Now, in order to do this, this electron has to move and collide and first reach here and then it will collide. So this is our collision number 1. After that, this electron will have some kinetic energy and it will start moving like this, and after some time it will also reach here and collide with this electron. This is second collision. So we have seen that there are 2 collisions in this, and the time between the 2 collisions is defined as relaxation time, that is tau. I hope you clear with this. This is just for understanding purpose. Now we will write force on an electron inside a conductor. Now, suppose if E electric field is applied, E is the electric field applied. And E is the charge on electron. So, the force on the electron will be only the magnitude is E times of capital E. Now, if the mass of electron is m, then this is the net force. Net force can be written by second law of Newton as mass into acceleration. And the acceleration of electron inside a conductor in which electric field E is applied is small e into capital E upon m. This is the acceleration of that electron. Now, if tau is the relaxation time, then the velocity attained by electron in this time will be written as by using v is equal to u plus at. And notice that acceleration here is constant because electric field is constant, charge is constant, and mass of electron is also constant. So velocity, now initially all the electrons were at rest, so u is 0 plus the value of a is E upon m, and the value of time is relaxation time, that is tau. So velocity will be E upon m into tau. Now this is the drift velocity, because this is only the velocity with which one electron is being collided with the other electron. So we can write this is the expression for drift velocity. Now let's try to generate the expression for current using V d is equal to E tau upon M. Suppose we have a conductor. This is a cylindrical kind of conductor having cross-sectional area equals to A. Now, it can be logically stated that if we take small volume inside this cylinder or conductor, then the rate at which this volume is being moved inside the conductor determines the intensity of current. That is, we can write it as I is proportional to rate of change of volume. Now, volume of cylinder can be written as this length, suppose this length is x, and into area of cross section. So I is proportional to d times of, so d of a into x upon dt. Since area is constant, it comes out of differentiation. It becomes a into dx by dt, where dx by dt is the velocity of this travel, and we know that it is equal to vd. So I becomes proportional to avd. Now, removing this proportionality sign, we will write I equals to some constant, and that constant equals to the charge. Suppose n is the free electron density inside this volume, then the total charge will be Ne, as we have seen from electrostatics, and hence the expression for current becomes NEA Vd. Now this is also an important relation between current and drift velocity. Now we can quickly take up an example to illustrate this formula. Now, the question is like, an electron beam has a aperture of 1 millimeter square. A total of 6 into 10 to the power 16 electrons go through any particular cross section per second. We have to find current and current density. First of all, we have to think about a formula for current in which aperture is being used, that is the cross sectional area, and number of electron, that is the electron density. So we have just seen a formula that I equals to NEAVD. For this, everything is known except this Vd, and for Vd we require many more parameters like electric field, relaxation time, and also mass of electron is known, but we don't know the electric field value and the relaxation time, so we can't use this formula here. So let's go from basics, that current is total number of charge flown in total number of time, that is in total time. Now, from this information, electron beam has aperture and a total of this much electrons. So we have directly given that this much of charge is being passed. So if 6 into 10 to the power of 16 electrons are being passed, then the total charge will be this charge, this number into charge on one electron, that is 1.6 into 10 to the power of minus 19. You can also write by Q equals to NE. This is Q equals to NE only. Upon, since we are given that analysis is to be done per second, so we will see this in 1 second. From this, the current will come out to be 9.6 into 10 to the power minus 3 ampere, or we can say 9.6 milliampere, which is also written as mAh. Now, we are able to get the value of current. Now, we also have to find the current density. Now, let's first look up what is a current density. Now, current density is it is denoted by J, and this is a vector quantity, so it's J vector. Now, it is a vector quantity and it is defined as the charge per, or else current per unit area, or else in form of charge we can write the charge per unit area per unit time. Is called current density. Now, two important points that to be remembered is that the current density and electric field has same direction. Another point to be remembered is the area is taken normal to the current. Hence, mathematically, J vector is defined as current per unit area. Now, as we have seen what is current density, let's now solve that problem. In this, we have to find the current density, and we are given. Now, we have calculated first of all the current. Now, we can easily find the current density because the area is given. So, current density J, or J vector, is current per unit area. That is, the current is 9.6 into 10 to the power minus 3 ampere upon the value of area is 1 millimeter square. That is 1 millimeter square. Or this can be written as 9.6 into 10 to the power minus 3 upon 10 to the power minus 6 ampere per meter square. So, this becomes 9.6 into 10 to the power 3 amperes per meter square. So, this is the current density. Now, let us move to our next topic, which is resistance. So, by definition, it is the obstruction caused by a material to the flow of electric charges. It is always required between 2 points. Let us suppose this is point P and this is point Q. Then The resistance between 2 points, that is R, is proportional to the length of this section. The more the length, the more there will be atoms present in the material and more will be the collisions. So more is the resistance. Similarly, it also depends upon the area of cross section of the material, and it depends inversely on the area, as the more the area, the more the space available for the electron to move. So the more the area, the more the space, lesser the resistance. Combining these two factors, we will get R is proportional to L upon A. Removing the proportionality sign, we will get R equals to rho L upon A. Now we will see what are these terms in this expression. Here R is the resistance. Resistance, it is denoted by this letter sigma, capital sigma, and its SI unit is ohm. Rho is the resistivity, and it is the property of material, and it is independent of the shape and size of any body, whereas resistance R depends upon the length and the cross sectional area, that is, it depends upon the geometry of the material. Rho is, and resistivity is independent. Its SI unit is ohm meter, ohm into meter. Now L and A are the length and area of the section. Now let's mention that very important point, that R, or we can say resistance R, is dependent on the geometry of the body, whereas resistivity rho is independent of the shape and size, and hence we can say rho is the unique property of a material, This is very similar to the density. Now density rho, this rho and this rho, symbols are same, but we are taking just an example that uh, density is the mass per unit volume of any substance. But if we fix a particular substance, let us say oil, the moment we change the mass, volume will be automatically changed, but rho will remain always constant. It will be changed only when we change the material from oil to some other material, say water. So the density of water and oil are different, but for any amount of mass taken for a particular substance, the density will be constant. So in that case, or in that way, similarly, resistivity is the property of a material which is independent of the size and shape. Also, we will write resistivity is also called specific resistance. Let's demonstrate this with an example so that the resistance become clear. Now suppose we have a material like this. Now, first of all, the resistivity or the specific resistance is constant for any part of this material. Let's suppose that is rho. Now, first part of the question is the resistance between these two faces. The second part of this question is the resistance between these two faces, and the third part is the resistance between these two faces. Now, let's write. Let's suppose if this is phase A, this is phase B, this is phase C, this is phase D, this is phase E, and this is phase F. First part is asked for resistance between AB. Second part is asked for resistance between CD, and third part is asked for resistance between E and F. So let's go by part. Recalling the expression for resistance, it was rho L upon A, because resistance increases if length increases and resistance decreases if area increases. So, how we will apply this concept in this part? Let's see. For our A part, the resistance between A and B. So, if we consider this, then the electrons will have to travel through this part. Now, what will be the length of flow in this part? Obviously, this length A will provide the resistance. So, resistance of AB part will be rho into A upon what is the cross sectional area, because since during traveling from this path, the total cross sectional area available for the electrons is this one, which is C times of B. So we will write upon C times of B. So this is the expression for resistance between A and B. Coming to our second part, which is resistance between C and D. Now, if we consider C and D, now the electrons will have to travel along this path. Now, which length will be responsible for providing the resistance? That is along this length, which is C. So, in this case, rho times of length is C. And what is the cross sectional area available from traveling from C to D, or else we can say D to C? That will be this much. That is whole of this area. So, just imagine that this area is available for electrons to travel from C to D. And what is this area? This is A times of B. Hence, the area of cross section is A times of B. Now, finally, our third part, resistance between E and F. Now, in case of E and F, this is E and this is F. The electrons will have to travel from this along this length. Now, which length is responsible for providing the resistance? That is B. So, in that case, the resistance will be rho into B upon what is the cross sectional area available? That is this part. What is the value of this area? It is C times of A, because this is C and this is A. So, it is C times of A. So, cross sectional area becomes C times of A. Hence, we can say just by changing the faces or the two points between which the resistance is to be calculated. The whole values of resistance changed, and it depends upon the dimension. So resistance is dependent upon the geometry of the substance taken, but resistivity is always constant. Now let's move to our next topic, which is effect of temperature on resistance. Now, why does resistance depend upon temperature? For this, suppose this is a conductor and there are many electrons present inside this conductor. Now, we have also studied the thermal or random motion, which was due to the temperature, as the name itself suggests, thermal. So, what happens if we raise the temperature? If we raise the temperature of the conductor, what happens is each of these electrons will gain some more kinetic energy. So, all these electrons will start to move randomly in all possible directions. And hence, since the velocity or the kinetic energy is also high, in this case, we will write if temperature increases, kinetic energy increases, which will result in more randomness, more randomness. And hence, when we apply electric field across this conductor, what happens is, if electric field is like this, the electrons will resist even more to travel in this direction. Let's change the pen, that is in this direction. So we can see one force is here and another velocity is here. So the net will be somewhere around here. So the whole point is, if the initial kinetic energy of electrons is more, in that case, even if we apply electric field, it will be very hard for the electric field to direct the electrons in a particular direction to produce current, which means the resistance is increased. It is less directed electrons, and hence more resistance. Now this is just for understanding purpose and we won't go in the derivation of this. But if we change if we raise the temperature of conductor, the resistance becomes R0 times 1 plus alpha delta theta, where R0 is the initial resistance, delta theta is the raise in temperature, and alpha is the coefficient of resistivity, or we can say resistivity, which is also called thermal coefficient of resistivity. Both are same. So we can see if temperature is raised, delta theta is theta final minus theta initial. Final, if temperature is raised, that means final temperature is greater than initial temperature. So this is positive. If this is positive, 1 plus some positive quantity becomes greater than R0. Hence, resistance is increased if we raise the temperature. Now let's quickly apply this on a concept through a problem. And the problem is like, The question says the resistance of a thin silver wire is 1 ohm at 20 degrees Celsius. The wire is placed in a liquid bath and its resistance increases to 1.2. What is the temperature of bath? So, since here the resistance is being changed because of the change in temperature, we use R equals to R naught 1 plus alpha delta theta. Now, what is final resistance given? That is 1.2. 1.2. What is the initial resistance? It is 1 into 1 plus the alpha is given to be 3.8 into 10 to the power minus 3 into, let's suppose this is delta theta only. So solving this becomes 1.2 minus 1 upon 3.8 into 10 to the power minus 3 equals to delta theta. Solving this, the value of delta theta becomes 52.6. Now this is the change in the temperature observed, and the change in temperature is final temperature theta final minus initial temperature, that is theta initial. This is given to be 52.6 and the initial temperature was 20 degrees Celsius. So the final temperature would be 52.6 plus 20, which is 72.6 degrees Celsius. Now I hope this topic is also clear to you. Now we will start Ohm's law. Ohm's law. According to Ohm's law, there are some materials for example metals or conductors which current passing through them is proportional to the potential difference applied across them. Now, according to this law, there are some materials for which the current passing through them is proportional to the potential difference. Now, from this statement, we can write the current passing through them I is proportional to the potential difference between them. Now, this can be written as V equals to IR. Now, note that this is not a Ohm's law, but it is mathematical relation between current I, resistance R and potential difference V. Now, in the statement we have seen that there are some materials. So, we will write such materials which obey Ohm's law are called ohmic devices. devices, and the other materials which do not obey Ohm's law are called non-ohmic devices. Now if we try to plot the current and potential difference, we will get, if this is V and this is I, we will get some straight line, and the slope theta, that is tan theta, is equal to the resistance of the material. Now non-ohmic devices will look like this. In that case, the relation between voltage and current is something but not straight line. But here also V is equal to IR is valid. Let's see. Suppose if this is point 1 and this is point 2, the potential here is V2, the potential here is V1, the current here is I1 and the current here is I2. We can write here also that V2 is equal to I2 R2, and also V1 is equal to I1 R1. But R1 is not equal to R2 because resistance is not constant and slope is changing everywhere. So slope gives the resistance, but this is for non-ohmic devices, and this is for ohmic devices. I hope this is clear. Now let's discuss some problems in order to boost confidence. The question is like this. A wire of resistance 100 ohm is melted and recast with double the length. What will be the resistance of the wire now? Suppose we have this wire initially which has the length L and its resistance is 100 ohm. Finally, the length becomes L or twice of L. But we can see if we increase the length, then the cross-sectional area has to decrease. But volume will always remains constant because mass can neither be created nor be destroyed. And hence, we will equate initial volume to the final volume. Initial volume, suppose this area is A, or else it is A1, and let's suppose this is A2. Then initial volume is A1 into L, and the final volume will be A2 into twice of L. So from this we get that final area A2 is half of initial area. Now using a resistance relation as rho equals to R equals to rho L upon A, which means a resistance is proportional to length upon area. From this we can say R1 upon R2 equals to L1 upon L2 into A2 upon A1, and we can say that R2, that is final resistance, L2 is the final length which is twice of L. L1 is initial length which is L, L2 is final length which is twice of L. Now A2 is the final area which is half of the initial area, that is A1 upon 2, and this is also A1. So this becomes 1 upon 4, which confirms that R2 is equal to 4 times of R1. So if R1 is 100, R2 becomes 400 ohms. Now this is the answer, but we can see conceptually also that since the length of the wire is increased and the area is in turn decreased, so the area of pass of for the electrons is lesser, so all the electrons will try to go through this length, and since the length is increased, there will be more number of collisions, hence increasing the resistance, and hence we can see that resistance is actually increased. Now we will take last problem for this lecture. A tapered shaped conductor is shown in the figure. The resistivity of this conductor is rho. The smaller radius is A and the larger radius is B. We have to find the resistance of this cone or this shape between these two faces, that is phase A and B. Now first of all, it should be clear that integration is involved in solving this question. Why? Because the resistance will be rho times of length into A. Between these two faces, even if we know the length, that is L, still the area is changing with every point traveling from A to B. So we have to do the integration. What we will do in the integration? We will take up a small element and write the resistance of this part, which is a type of disc. Now let's suppose this inclined surface meet somewhere at point O, and let's clean up these diagrams and we will draw neatly. Now let's suppose we take up an element at a distance x, and this thickness is dx. Suppose the radius of this disc is r. Now in our electrostatic course also, we have discussed the method of doing integration properly, but let's, for the sake of the students to revision, let's discuss one more time. Now as we know, during integration, once we take up one element, we have to forget everything else for some time and just focus on our element. So let's draw this neatly. At a distance x, we have a disc having some thickness dx and radius r. If we try to write the resistance of this section, what will be? Dr, because it is an elementary particle. Resistivity is independent of the shape, that is rho. The length of this part is dx. Why? Because L is the length from which the current passes. So with respect to this element, the current will pass like this. So it will have to travel a distance of dx upon, what is the area of this section? The area of cross section is pi into r square. Now in order to get the whole resistance, rho is constant, pi is constant. We have to get r in terms of x or vice versa. For getting r in terms of x, let's focus on this diagram. Suppose this angle is alpha. We can see that tan alpha will be written as tan of alpha will be written as A upon, let's suppose this point is C. So tan alpha is A upon OC, and also tan alpha is from this big triangle, tan alpha is B upon, suppose this point is D, so it is OD. Now OD can be written as L plus OC. So let's solve this equation. This becomes A by OC equals to B by L plus OC. So this becomes L plus OC upon OC is equal to B upon A. L by OC equals to B upon A minus 1, which is B minus A upon A. So OC becomes AL upon B minus A. Now we will see why we have calculated this length OC. Now as OC is known, now we can apply the value of tan theta or tan alpha in this triangle. Hence, in this triangle, the value of tan alpha will be R upon, if this point is X, R upon OX. So the value of tan alpha is R upon OX, and OX is simply OC, that is this distance, plus X, that is this distance. So it is OC plus X, and now we have calculated OC. So this becomes R upon AL upon B minus A plus X. Now this equation can be rewritten as AL upon B minus A plus X equals to R cot alpha. Now our expression for resistance was dr equals to rho dx by pi r square. Dr equals to rho dx by pi r square. Now let's substitute the value of dx. How we will calculate the value of dx is that we will differentiate this equation and we will get 0, because this whole term is constant. So differentiation is 0. 0 plus dx equals to dr cot alpha. Since cot alpha is also constant, so in place of dx we can write dr cot alpha. So this becomes rho into cot alpha upon pi dr upon r square. Simply integrating this equation. Now we have to cover all the elements. Now when the element was at this position, that is x equal to 0, in that case what will be the radius of that disk? That would be a. And when this x becomes its maximum value, that is L, in that case what will be the radius of the disk? That will be b. So if we put the limit of r from a to b, all of this shape, tapered shape, will be covered. So the limits will be a to b and the resistance will be 0 to r net. Solving this, we will get r net equals to rho cot alpha upon pi minus 1 by r. This becomes a to b, which is rho cot alpha upon pi 1 upon a minus 1 upon b. Now this is the final expression, but since alpha is the value that we have assumed in the question, we have to eliminate this. So from this triangle we can write the value of cot alpha. The value of cot alpha will be base upon perpendicular, where base is OC upon perpendicular is A. So OC upon A. What is OC now? OC is AL upon B minus A. AL upon B minus A into 1 upon A, which is, let's remove A, so this becomes L upon B minus A. So put the value of cot alpha at rho by pi. The value of cot alpha is just calculated L upon B minus A. So it is L upon B minus A. Now this can be rearranged as B minus A upon AB. So we can see that this denominator as numerator is getting cancelled. So this becomes rho L upon pi AB, which is exactly our answer. Now this problem is taken from a very popular book called H.C. Verma. Now many such problems you can practice from that book also, and also you can download our app FosterJEE from Google Play Store or Apple Store. Now I will give you one more problem for your homework. Now that problem is, now in this problem we have a cylinder from which a hollow cavity like this is being taken out. Now the radius or the inner radius of this cylinder is A and the outer radius is B. The material has the resistivity rho, and we have to find if this is the face or the inner face, suppose I, and this is the outer face. So the first case we have to find the resistance between inner face and outer face. So the current will flow in radial direction, in all possible direction, from all possible paths, and we have to find the resistance between inner and outer part. And in our second case, if this is face A and this is face B, then resistance between A and B is to be calculated. Assume this length as L. Now I want all of you to attempt this problem, and we will see this solution in our next lecture. Thank you.